Hi, this is Lab 2, Motion of a Falling Object. For this lab, I recorded a ball of socks being dropped from at rest and falling down, and I analyzed this motion using Tracker. I then made two VPython models made to predict the motion that I recorded, and the first model I made incorporated only the weight force acting on the system, and the second one I made incorporated both the weight force and the drag force acting on the system. I then compared the predicted motion to the observed motion and found that the drag force definitely does have a considerable impact on the velocity of the system. So the fundamental principle is Newton's second law. From this we derive the weight force equation, which is negative m times g, and the drag force equation, which is drag force equals b times velocity squared. It's important to note with this that drag force is opposite to the velocity, and since the velocity of our system points in the same direction of the gravity force, that means that the drag force will directly counteract the gravity force. So here's a tracker video that I made that I analyzed. It's a ball of socks starting at the origin and falling towards the negative y direction, and it starts at rest. And then the position versus time data was plotted right here in this curve and charted right here in this chart. And here's the VPython model that I made to predict this motion. This one using the drag. It's important to note that as the drag increases as the velocity increases, and this is apparent through the equation, which says that the drag force is proportionate to the velocity squared, and also apparent through the equation is that the weight force is constant for the system. And so in order to obtain this model, here's the coding that I used. On the left hand side is the initializations, the important one being the initial velocity, which is 0 since it was at rest, and on the right hand side is the actual physics, and here the W is the weight force, and that's that equation, and here's the drag force equation, and the summation of those two forces is set to be the net force, and then that's plugged into Newton's second law, and reiteration of that results in the motion prediction. And down here is the B, which is the proportionality constant in the drag force equation, and that was an unknown value to me since that's unique to each system. And so I found that empirically by plugging in random values for V until the final Y value from the model approximately equal the final Y value from the tracker video observations. So here are the graphs that I obtained. The blue line is the model with no drag, and as expected, that predicted a much higher velocity than I observed. That's because there was no drag to counteract the force, so the velocity was higher. And then the red line is the model with drag, and that also overpredicted the observed velocity of the ball dropping, but it's much closer than the model with no drag still. And this little discrepancy may be due to technical error, such as the ball of socks became a blur in the video after a while, but it's still a pretty good prediction. And so here are the questions relating to the lab. Terminal velocity is defined to be when drag force equals weight force. And so the blue line, that was a model that didn't incorporate drag force, so that won't reach a terminal velocity, but the other lines will eventually. And because the forces cancel each other out, the net force will equal 0, and that means that final velocity will equals initial velocity. And so we didn't quite observe that, but given enough time, that would have happened eventually, and those slopes would have been straight, and that one of the blue model prediction without drag would have kept on increasing the slope. And then the other question is if the socks had been thrown down, then the position versus time graph will look more like this one on the right rather than this one on the left, which is the one that we actually obtained for the model. The one on the right is basically just showing that terminal velocity would have been reached at an earlier time, but the overall terminal velocity will still end up to be the same since that value is not dependent on the initial velocity. So in conclusion, since drag force and weight force in this case cancel each other out, when they're equal to each other, that means that net force will equal 0. And as we learned in the last lab, when net force equals 0, that means that the system will travel at a constant velocity.